Can you define most of the physics in a single word? I can, and that word is ratio. We begin with something simple, time, and from there, using nothing but ratio, we build the entire language of motion, speed, velocity, acceleration, even projectile motion, exactly as Galileo once did. No formula at first, no memorization, only pure discovery. So let's continue this journey and we ask ourselves a very simple question. What is time? Turns out, time is just change. Change in your environment related to other things. When the sun moves across the sky, time moves. When the seasons shift, time shifts with them. Even when a nerve fire inside your body, that's time too. Time is not a thing. Time is a measure of change. And if time is a measure of change, then it's a ratio. In time, the change and the reference are often the same kind of thing. But in distance, we compare a position change to a unit we have defined separately, like 1 meter or 1 kilometer. In time, both change and the reference are the same entity, but in distance, the reference is something external. That difference makes distance and time feels fundamentally different. But here's where things get interesting when we put them together, because in the moment when you compare how much distance changes to how much time passes, you have just taken your first step into describing motion. Imagine watching a runner. In 1 second, they cover 5 meters. In 2 seconds, 10 meters. Distance divided by time. That's speed. A simple ratio that tells us how fast something moves, but not where it headed. Now, if we include direction, say 5 meters east every second, that's when speed transforms into something richer, velocity. Velocity is speed's smarter cousin. It tells you how fast and exactly where you are going. But motion doesn't stay the same. Maybe the runner starts slow, then speeds up. When velocity itself changes over time, we call that acceleration, where u is the starting velocity, v is the final velocity, and t is the time taken. This isn't just a formula, it's another ratio, another block. Keep stacking them, and you get jerk, snap, crackle, pop, whole layer of changes. Now with all these pieces, we are ready to predict the path of falling star or a cannonball, just like Galileo did. When you throw a ball forward, it doesn't just fall straight down, it moves forward and down at the same time. Galileo's genius was to split this complex motion into two simpler parts. Horizontally, there's no acceleration. Speed stays constant. Vertically, gravity pulls the ball downward, causing constant acceleration. Let's find the vertical distance using our ratio ideas. First, acceleration tells us how velocity changes over time. Starting from rest means initial velocity u equals to 0. So after time t, velocity is a times t. Now, to find how far it moves vertically, we multiply velocity by time. But velocity isn't constant. It starts at 0 and grows to v. So, what velocity should we use? The answer, the average velocity. With constant acceleration, velocity changes linearly over time. So, the average velocity is halfway between start and end. And as you know, when you multiply velocity by time, you get displacement. And that's exactly what we are trying to find. Horizontally, the displacement is x equals to u times t. So time can be written as x by u. Substituting this into the vertical displacement formula gives an elegant equation. Notice what this means. Horizontal motion and vertical motion are independent, yet together they create this elegant parabolic arc. That's the magic Galileo revealed. Two simple motions combining into one graceful path. And all this magic comes from stacking simple ratios, no complicated math needed. So we began with distance and time and ended up describing the motion of falling stars and flying arrow just through ratios and our imagination. This video is part of our Ratio Like Never Before playlist. You can find it right here. And if you find this video valuable, please hit the subscribe button. Thanks for watching.